So in our next lecture, we're going to begin Chapter 10 and look at hypothesis testing, specifically regarding parameters or the data that's connected to a population versus a sample. Here we're going to be determining the null and alternative hypotheses, explaining different kinds of errors, and then how to state conclusions. There's a very formal way of doing that for hypothesis tests. So let's start it from a conceptual perspective. Sorry, maybe I shouldn't record this video now. So let's look at an example. Example, is your friend cheating? A friend of yours wants to play a simple coin flipping game. If the coin comes up heads, you win. If the coin comes up tails, your friend wins. Suppose the outcome of 5 plays of the games is tails, 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 and you want to know, is your friend cheating? So we need to determine the probability of getting 5 tails in a row so we can compare that probability to what actually happened, as we've done in previous sections. The flips of the coin are independent, meaning each flip has no impact on the next flip, etc. So 5 tails in a row is the probability of flipping a tails on one toss and then that same flip for the next toss for 5 times. Well, the probability of getting a tails on each flip is 1 out of 2. There are 2 choices and tails is one of those outcomes. So we get 1/2 to the 5th power, which is 0.03125. It's a pretty low percentage, 3% of the time. So if we flipped a coin 5 times for 100 different experiments, we would expect about 3 of the 100 experiments to result in all tails. So what we observed is possible, but not likely. So you can make one of 2 conclusions. Your friend is not cheating and happens to be lucky, or your friend is not using a fair coin. That is, the probability of obtaining a tail on one flip is greater than 1/2 and is therefore cheating. So is your friend cheating, or did you just happen to experience an unusual result from a fair coin? This is at the heart of hypothesis testing. We make an assumption about reality. In this case, the probability of obtaining a tail is 1/2. We then look at or gather sample evidence to determine whether it contradicts our assumption. Determine the null and alternative hypotheses. An hypothesis is a statement regarding a characteristic of one or more populations. In this chapter, we look at hypotheses regarding a single population parameter or data point. Hypothesis testing is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more populations. The null hypothesis, denoted H0, which is that sub-zero there, is a statement to be tested. The null hypothesis is a statement of no change, no effect, or no difference, and is assumed true until evidence indicates otherwise. The alternative hypothesis, denoted H1 or H1, is a statement that we are trying to find evidence to support. The steps in creating hypothesis testing is to make a statement regarding the nature of the population. Then collect evidence, sample data, to test the statement. And 3, analyze the data to assess the plausibility of the statement. The null hypothesis is a statement of status quo or no difference and always contains a statement of equality. The null hypothesis is assumed to be true until we have evidence to the contrary, and we seek evidence that supports the statement in the alternative hypothesis. Okay? This will become more clear In this chapter, there are 3 ways to set up the null and alternative hypotheses. So the first way is equal versus not equal hypotheses, okay? And this is when the null hypothesis says that a parameter is some value. So for example, we might say the average income of adult Americans is $65,000, okay? Then the alternative hypothesis would be the average income of adult Americans is not $65,000, okay? This is called a two-tailed test because we're using not equal. Equal versus less than. This is called a left-tailed test. Here, again, the parameter is some value, and then our alternative hypothesis is that it's less than that value. So using that same example, the average income for adult Americans is $65,000. The alternative hypothesis would be the average income for adult Americans is less than $65,000. This is very straightforward. As you can see, it's very logical and kind of follows it. And as always, examples tend to make things easier to understand. And so the right-tailed test is just similarly, but with greater than, right? So in this case, the alternative hypothesis would be the average income in for American adults is greater than $65,000. Again, the null hypothesis is a statement of status quo or no difference and always contains a statement of equality. Adult Americans' average income is $65,000, equals $65,000. That's the statement of equality. The null hypothesis is assumed to be true until we have evidence to the contrary. So we're assuming that the average income is $65,000 until we can conduct an experiment, a survey, etc., to collect data to disprove it. Okay? And so what we're doing is we're seeking evidence that supports the alternative hypothesis. One-tailed test. Left and right-tailed tests are referred to as one-tailed test. In the left-tailed test, the direction of the inequality sign points to the left or less than. In the right-tailed test, the direction of the inequality sign points to the right or greater than. In all 3 tests, again, the null statement contains a statement of equality. The mean is this. The number of Americans who make less than $20,000 is 30%, something like that. So let's look at an example. Determine the null in a hypothesis test and then state whether the test is two-tailed, left-tailed, or right-tailed. So our first example is the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics, experience headaches as a side effect. A researcher for the Food and Drug Administration wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. Okay? This hypothesis deals with the population proportion, P, right? What is the proportion of, 2-year-olds? Of children who take the medicine and whether it's greater than 2%. If the new drug is no different from competing drugs, the proportion of individuals taking it who experience a headache will be 0.02 because 2%, right? This is the statement of no effect. This is our null hypothesis, okay? We want to determine if the proportion of individuals who experience a headache is more than 2%. This is the statement we are attempting to find evidence to support, which is our alternative hypothesis. So our null hypothesis is the proportion of individuals taking the new drugs who experience a headache as a side effect is 0.02. That's our equality statement. And the proportion is equal to 0.02. Our alternative hypothesis is that the proportion of the individuals taking the new drug and experience a headache is more than 0.02. And you can see here on the right the equality statement for the null hypothesis and the greater than statement for the alternative hypothesis. This is a right-tailed test. Notice it points to the right, and it includes a greater than symbol. So that's an easy way to remember that greater than points to the right, as long as I've got my directions. Let's look at another one. The Blue Book price of a used 3-year-old Chevy Corvette Z06 is $59,083. Grant wonders if the mean price of a used 3-year-old Chevy Corvette Z06 in the Miami Metroplex area is different from $59,083. This hypothesis deals with the population average or mean. If the mean price of a 3-year-old Z6 in Miami is no different from the Blue Book price, then the population mean in Miami will be $59,083. This is the statement of no difference. This is our null hypothesis. Grant wants to know if the mean price is just different from $59,083. He doesn't ask if it's more or if it's less. He just wants to know if it's different. This is the statement we are attempting to find evidence to support. This is our alternative hypothesis. And again, you can see them here. The null, the mean price of a 3-year-old Corvette in Miami is no different from the Blue Book price, $59,083. I don't really like the way they've written that. I would say that the mean price is the same as the Blue Book, $59,083. When you add all these negatives, and sometimes you have to do it for formality, but negatives in sentences can create difficult understanding. So if you look on the right, we're saying the null hypothesis is the mean in Miami is equal to $59,083, which is the Blue Book value. So I don't see any reason to word this the way that they've done. It's not different from the mean. I think I would, again, make it a positive or a declarative statement, not a negative declarative statement. The alternative hypothesis by nature needs to be a different statement. So the mean price of a 3-year-old Corvette in Miami is different from the Blue Book value. So to me is they're trying to mirror these statements, but to me they make them more confusingly because they almost seem the same because it's different from the Blue Book value in both of them. So again, I would reword the null hypothesis to say that it's the same, and then the second, the alternative, is that it's not, that it is different. And you can see that it doesn't equal, okay? This is a two-tailed test because the alternative hypothesis contains a not equal, okay? Our last example, that's not our last example. That's our last example, okay? The standard deviation of the contents in a 64-ounce bottle of detergent using an old filling machine is 0.23 ounce. The manufacturer wants to know if a new filling machine has less variability. So here you have a manufacturer who's trying to make more consistent the level of contents that they put into a bottle of detergent. Okay, so here the hypothesis deals with the population standard deviation. If the new machine is no different from the old machine, the standard deviation of the amount in the bottles filled with by the new machine will be 0.23 ounces. This is the statement of no change, our null hypothesis. The company wants to know if the new machine has less variability than the old machine, okay? It might seem that it's different, but no, the question is it less variable? Is the standard deviation less in a new machine? This is the statement we're attempting to find evidence to support, which is our alternative hypothesis. So again, we have our H naught, our null hypothesis, as the standard deviation is no different from the old machine, 0.23 ounces. Again, I would not write it that way. And we can see the statement of equality symbolically, standard deviation equals 0.23 ounces. Our alternative hypothesis is the standard deviation in the amount in the bottles is less than the old machine. And you can see the less than symbol here pointing to the left, which makes this a left-tailed test. Okay, so hopefully those have helped kind of you figure out how to do a null hypothesis and an alternative hypothesis that we're going to be testing. Okay. So our second objective is to identify type 1 and type 2 errors. And there's a nice little table from your book, figure 1 in this section, that explains how these are. And so in words, I'm going to combine them. So if we reject the null hypothesis, when the alternative hypothesis is true, this decision would be correct. Okay? We reject the null hypothesis. Let me see this. We reject the null hypothesis when the conclusion, this is reality, so this is the null. We reject the null when the alternative is true. Reject the null when alternative is true is the correct conclusion. That's here at the bottom right. Okay? We do not reject the null hypothesis when the null hypothesis is true. This is the top left. Don't reject the null if the null is true. Okay, this is also a correct conclusion. We reject the null when the null hypothesis is true. Reject the null when the null is true. This is a type 1 error. This decision would be incorrect. Reject null when null is true. A type 2 error would be we don't reject the null when the alternative is true. Okay, and this would also be incorrect. Okay. Type 1 is all about null. Reject null when null is correct. Type 2 has both of them in it, has both hypotheses, has two hypotheses in it, and is a type 2 error. We don't reject the null when the alternative is true. Okay. Notice both of these are the subject to a true hypothesis, whether it's the null or the alternative. And then we're talking about rejecting or not rejecting the null hypothesis. So hopefully that those details help the construct of this and help you memorize and retain this knowledge. Type 1 is all about the null, one type of hypothesis. Null is rejected, but the null is true. Type 2 has two hypotheses. We're dealing with both of them. We don't reject the null when the alternative is true. So let's look at an example about type 1 and type 2 errors. The Medco pharmaceutical company has just developed a new antibiotic. 2% of children taking competing antibiotics experience headaches as a side effect. This is the same example. A researcher for the Food and Drug Administration wishes to know if a percentage of children taking the new antibiotic who experience a headache or a side effect is more than 2%. Explain what it would mean to make a type 1 error. Now remember, a type 1 error uses only one hypothesis, the null hypothesis. And so the conclusion is that the null hypothesis was found to be true. Now, do we reject or accept it? Well, if it's found to be true, an error would mean that we reject that null hypothesis, okay? This is stating the null hypothesis, which is that the proportion taking the new drug is 2% or 0.02, and that the alternative hypothesis is that the proportion for the new drug is greater than 0.02. Okay, and there's our reality there as well, our table for the type 2 errors, correct or not. I should have left that off actually until the end, but that's okay. So again, our first a type 1 error is made if the sample evidence leads the researcher to believe that p is greater than 0.2. That is, we reject the null hypothesis when in fact the proportion of children who experience a headache is not greater than 0.02. So we're saying that we reject the null hypothesis when the null hypothesis is true. Again, that's a type 1 error, only using the null hypothesis. The type 2 error is that we use both hypotheses. Again, the conclusions are about, as we saw in the last, if we think of it that way, that the alternative is true. And so if the alternative is true and we still accept the null hypothesis, not reject it, then this would be the type 2 error. A type 2 error is made if the researcher does not reject the null hypothesis that the proportion of children experiencing headache, when in fact the proportion of children who experience a headache is more than 0.02, which means the alternative is indeed true. The sample evidence led the researcher to believe p equals 0.2 when in fact the true proportion is some value larger than 0.02. Okay, so type 1 involves just the null hypothesis, and type 2 involves both hypotheses. Note, both of these are about whether we accept or reject a null, and so the front end is always the same. The probability of making type 1 and type 2 error. Alpha equals the probability of making a type 1 error. Okay, and that is, of course, the probability of rejecting the null when the null is true. Beta equals the probability of a type 2 error. This is the probability of not rejecting the null hypothesis when the alternative is true. Again, the way I remember these is that type 1 is focused on one hypothesis. Type 2 uses both hypotheses, the null and the alternative. The level of significance, alpha, which is the probability of making a type 1 error. This is alpha is called the level of significance. This is chosen by the researcher before the sample data is collected. And you're like, wait, what does that mean? Okay, if consequences are severe, in this case, children getting headaches, etc., that might be quite severe or quite risky, then the researcher should set alpha, or the level of significance, to be small, okay, 0.01, so as you want that probability to be very small if the impact of that probability has great consequences. Okay, if the consequences are not severe, a higher level may be chosen, for example, 5% or 10% or 0.05 or 0.10. If again it's not such a, in this case you're talking about the health of a children, which would make it seem much more consequential than perhaps, I don't know, how people spend money on their vacation or something like that. Okay. As the probability of type 1 error increases, the probability of a type 2 error decreases, and vice versa. So that's kind of interesting as well. Our last objective here is just how do we state conclusions to hypothesis tests. Notice we never accept the null hypothesis, okay? Because without having access to the entire population, we don't know the exact value of the parameter stated in the null hypothesis. Rather, instead of saying we accept the null hypothesis, we say we do not reject the null hypothesis. This is like the court system. We never declare a defendant innocent, but rather say the defendant is not guilty. So let's look at our final example here. The Medco pharmaceutical company has just developed a new antibiotic. 2% of children taking competing antibiotics experience a headache as a side effect. A researcher for the Food and Drug Administration believes that the proportion of children taking the new antibiotic who experience a headache as a side effect is more than 2%, or 0.02. From a previous example, we know the null hypothesis is, I don't know where the rest of that went, that the percentage of children taking the new medication 2% of them are 0.02. The proportion that get headaches will be 0.02. And you can see that here in symbols. Suppose that the sample evidence indicates that the null hypothesis is rejected, state the conclusion. So this is for part A. The statement in the alternative hypothesis is that the proportion of children taking the new antibiotic experience a headache as a side effect is more than 2. Because the null hypothesis is rejected, there is sufficient evidence to conclude that the proportion of children who experience a headache as a side effect is more than 0.02. Okay? Notice how we say that. Because the null hypothesis, the proportion equals 0.02, is rejected, there is sufficient evidence to conclude that the proportion of children who experience a headache as a side effect is more than that 2%. The second one is the null hypothesis is not rejected. How would you state that conclusion? Because the null hypothesis is not rejected, there is not sufficient evidence to say that the proportion of children who experience a headache as a side effect is more than 0.02. So notice this, really the stating the conclusion, it really starts after the comma. There is not sufficient evidence. And here as well, there is sufficient evidence. Really, the last phrases in these are the statement of the conclusion. Okay, so this was a light section, and hopefully you probably need a light section this deep into the course. So we're finished with this section, and we'll move on to section 10.2.